So, welcome back to my tomography class. So, last time the video came out kind of grainy, and yeah, so I just got this new camera, this Rebel SL3, and yeah, I'm still learning how to work the features and tweak it a little bit. So I had it on auto last time, and auto is almost always a horrible idea. But with children running around, I had my wife basically took children into a back room. It's like, you have an hour, get recording. And so I just sort of jumped into it. I wanted to have the intro video to be a little bit higher quality than what it ended up being, but that's just the way it goes. I shot grainy video at 4K, and that took 25 gigabytes. Not doing 4K again. Actually, I might be. Okay, I just checked. Maybe I am. I don't know. I think it's just doing 1080p. Hopefully. Otherwise, I'm gonna run out of space on this card pretty damn quick. Okay, so what are we going to be doing today? So today we're just going to be going through and doing the few lectures that I am dreading in this class, and that is setting up the physical motivation for what we're going to be doing. I am a mathematician, I'm not a physicist, I'm not a practitioner. I work with the tools of tomography, Fourier transforms, Radon transforms, and my own personal specialty, I work with kernel methods. And that's where my comfort zone is. And so these first few lectures are all going to be sort of outside of my comfort zone. I'm going to be kind of learning a lot of this stuff as I talk to you. But I'm just seeing the light at the end of the tunnel where I can start talking about the Fourier transform, and then that'll be a lot of fun for me and hopefully for you too. But why don't we go ahead and just get started? So the things that come up in medical imaging and say CT scanners in particular are X-rays. So these are emitted from some sort of emitter. I'll write something here, and then you have a receiver on the other end, and you have something in between, and so there's an intensity that comes out of the emitter, and the change in intensity is detected by the receiver. And what happens in the middle is that the middle mass attenuates the intensity, I think, and basically each little bit of particle, depending on the density, each chunk of mass is basically making a decrease in the intensity of the beam that is going through it. And so we're going to do a quick mathematical formulation of this. It can be represented as a differential equation, and so then you end up getting I think it's the log of the intensity that you start with divided by the intensity that you end at is equal to minus the integral through the medium of what we call the attenuation function, and more or less the idea is that that attenuation function is what we're going to be trying to approximate. So this is called Beer's law, and so we'll put that into lecture and talk about it a little bit more precisely than what I'm saying right here. And so then we're basically gonna be talking about all these integrals through people or objects or whatever you like, and so we need to talk about how we're going to be parameterizing these lines and these integrals, and basically what that's going to give us is it's going to give us a sort of a framework that we can go ahead and define the Radon transform with, and the Radon transform is defined in terms of polar coordinates. This polar coordinate setup gives us what we call a sinogram, and so we'll talk about plotting sinograms and sort of interpreting what they are. They're kind of basically if you take for any line, we basically have an initial point and an angle through that line. We're going to plot over the angles and then over the initial position, and between these two quantities you can sort of get sort of a polar graph of an object or integrals of that object. And so if you have a little dot or a circle, you basically see something that looks like a sinusoid as you as you go through. And so sinogram is more or less what you're going to get out of an X-ray machine. And then the idea is that we're going to be trying to take these sinograms and rebuild the original object based on them. And so that's going to be sort of the topic of the next section, where we're going to talk about the radon transform and a little bit of back projection. And then after that, then we get to go to the things I'm happy with, and that is Fourier transform. So, all right, that's enough jabbering for me, and we can go ahead and jump in.
Okay, so let's see if we can get through this smoothly. So what we're going to talk about today is basically, say, X-ray CT, the idea of it. I'm not going to tell you about the actual devices or whatnot, but it sets up a nice little numerical problem. We're going to talk about Beer's law, which has to do with sort of infinitesimal absorption and the differential equation that comes out of it. And then just after that, we're going to talk about sort of the inverse problem, and maybe not in that particular order, but this sort of sets everything up that we're going to talk about. And if we have time, we'll talk about the radon transform, but I'm not entirely sure we will. Okay, if anything, the next couple lectures will sort of give you a light touch of the radon transform and the Fourier transform before we dive into the much more functional analysis portion of this, where we're going to talk about the Schwartz space and distribution theory and whatnot. But in the meantime, we'll talk about X-rays and sort of give a light sort of introduction to what we're going to do in this class. So the general idea is that we have an X-ray of known intensity passes through what we're going to call a medium. So through a medium. Okay, and so this medium, it could be muscle, it could be a skeleton, could be brain tissue, and it could even be something like the book that I'm following here is Feeman, by the way. And so he likes to say a sarcophagus. And they're serious about that. Basically, and CT imaging is used in paleontology and other things like that in order to sort of see inside of objects that they don't want to actually break apart. MRI is great, but you have to worry about if there's a metallic object inside of a box, because one, it could blow out and destroy your MRI scanner, and on the other hand, but CT and radiation isn't really going to hurt anything that's already dead. So you can do really intense sort of CT scans, irradiate the heck out of it, but still see inside without really destroying the contents. And so CT is used a lot in that sort of case. And you can get rather good pictures out of that. With a human subject, you only want to expose them to a certain number of X-rays. So, but yeah. I guess, so we have a medium, and then we're going to say that basically some of the energy is absorbed by the medium. And basically the intensity of the beam is measured after it passes through the medium at the detector. Okay. Cool. And so then finally, the difference between the final and initial intensities, the final and initial intensities tells us how much the medium absorbed. Okay, so yeah, that's cool. So why don't we go ahead and talk about this a little bit. So basically, the idea is that you have an X-ray that's shooting out, boom, and you have some sort of subject here that you're trying to look at, and you have a detector. The detector could be like a sheet of phosphorus or something like that, or it could be a little bit more sophisticated, like what you see in a CT machine. And you don't see any real details except for the outline of what you saw. Although some parts are going to be lighter than others, so you might have like you can see I don't know. I don't even know what I'm drawing at this point, but basically at the other end you're going to have sort of differing intensities all across this detector, and that gives you an idea that maybe these lighter spots didn't absorb it quite as much, but these darker spots absorbed quite a lot and ultimately blocked the entire X-ray. And so so basically one say X-ray lacks depth. There's a lot of stuff in the way here, but you don't know where it was. You could have had another object just like sitting right between you and the subject, and you wouldn't be able to see it because this guy would have been in the way. So basically anything behind an object, blocking an X-ray, cannot be seen. It is occluded, if you want. Okay, so basically the principle of CT scanners is that if you take several X-rays at different angles, then you can use the multiple angles to get more information about the medium. Okay, so there you go. Yeah. So that the idea is that you would basically set up another shot here, and then you get another X-ray of the person. So it could be looking like this, and yeah, and so then you can use that differing angle as sort of to give you an idea of where some of these spots actually were. So you might have had this. Might have been in the back with this thing, and then this thing could have been, two things here, etc. So you can figure out where all those different, more transparent chunks of your medium are. And so the book, the Feynman book, actually has a cute example with a bunch of squares, and let's go ahead and talk about that. So, so just to give you an idea of the sort of information you're going to need. So this is a 9x9 grid, and we're going to say that we have, several of them are blank, so dark, and so we're going to say that each, let me give myself some more space, so each white box absorbs 1 unit of energy from an X-ray beam. Right. Man, that word got away with me there. All right, so beam. There we go. Okay, so so then what we can see is that if you take X-rays going through, say, these rows, and this one is going to absorb 2 units to absorb. This one absorbs 2. This one absorbs 1. Right, and you can say, let's say we're shooting vertically, and so let's see what we get. This one only absorbs 1 unit is absorbed. This one absorbs 2 units, and this one absorbs 2 units. Okay, so just using the information that we have from here, so using the first row, we get 3 possibilities. I can't spell possibilities, apparently. Seems like half this lecture is me spelling things weird. Okay, so what do we get? So so what are the possibilities we have here? So on the first row, since we know that there are 2 absorptions and we only have 3 spaces, then one of those spaces has to be empty. So it could be one of these 3 possibilities. Okay, so just using that information here, say using the first row absorbing 2 units. So since we know that the first row absorbed 2 units, we can make this guess initially. And then you can see that if you add more information, that you can lock down, you can reduce the number of possibilities for this row. So for instance, so let's say now consider the first column absorbs 1. Right, and so this reduces the total number of so the total number of possibilities just for, like, these 2 rows would be, say, 32, right? Possibilities. Now, just using this one, we went from 8 different possibilities just for the first row to 3, just using the 2 absorb. So we're using this information to reduce the number of things that we need, configurations we need to consider. And so between these 5, that would be 32 possibilities, or 2 to the 5th. So what we're going to do is we're going to go ahead and try to use the fact that the first column absorbs 1 to reduce the number of possibilities. So let's see. All right, so we could have that the absorbing the white block was here, and then that would mean that these 2 would be blank. But since we know that the first row absorbed 2, then that means that there are 2 possibilities. Either this one's blank, or the other one is blank, because there can only be 2 white blocks in that column. Sort of a Sudoku that we're working out here, right? So it could be this way. Okay, so that's one option. Another option would be that the white block was in this space. And so that would leave this one dark and this one dark. Now, that leaves only one possibility left for these 2 blocks, and that's there. And so then if I were to say maybe the white block is the bottom one, then this is blank and this is blank, because the total sum of the column white boxes can only be 1. And then that again leaves that. So there are 4 possibilities here. Okay, so So using this information here and this information, what we found is that we only have 4 possibilities left over, and this is down from 2 to the 5th, or 32 possibilities. So using the sum of the first row and the sum of the first column entries, basically that reduced it considerably down to just 4 options. Okay, so then the question is, if I maybe what happens? Maybe is it enough to use the sum of the rows and then the sum of the columns in order to figure out what all of the entries are? And we can go ahead and take a look at that question. So let's go ahead and redraw this. Right? There we go. And so let's fill this guy in. Let's fill this guy in. And fill this guy in. And we had one more. This one. Okay. So then let's go ahead and start labeling these. So it's going to be x1. This one is going to be x2. This one is x3. This one is x4. This one is x5, x6, x7, x8, and here we get x9. Okay, so now let's take a look. So if I think about this in sort of a matrix notation, then let's see what we get. So we're going to basically be multiplying matrix, and we're going to get values out of it. So we have x1, x2, x3, x4, x5, x6, x7, x8, x9, and you can see it's sort of suggestive of what's going to happen here just by how the size of the things I drew. Shoop, shoop. All right. Okay, so let's see what happens. So the first, if we're summing the first row, we're summing x1, x2, and x3, then as a matrix, that's going to be 1, 2, 3, x1, x2, and x3. Just put in the columns here, x1, x2, x3, x4, x5, x6, x7, x8, and x9. All right, so we're going to add these 3 together, and what's left is everything else is 0. Okay. Then if I want to sum the next row, well, we're not using x1, x2, x3 anymore. We're using x4, x5, and x6. So we add those in. And then if I take a look at the last row, we're going to add those in. So it's going to be 0, 0, 0, 0, 0, 0. We're not caring about the first 6. But then we add 7, 8, 9. Okay. So now let's see. If I want to add the first column together, I get x1, x4, and x7. So that's going to be a 1 here, a 1 here, and a 1 here, and everything else is zeros. If I want to add the second column, that is x2, x5, and x8. So x2, x5, and x8. That was an 8 there. And everything else is 0, 0, 0, 0, 0, 0, 0. And if I want to add the last column, x3, x6, and x9, well, then it's going to be this. So it corresponds to x3, x6, and x9. Okay. So what were the answers that we would get? Well, adding for the first row, we get 2. We already knew that. Adding for the second row, we're going to get 2 again. Adding for the third row, we get 1. Adding the first column, we get 1. Adding the second column, we get 2. And adding the last column, we get 2. Okay. So this is a cute way to start. But immediate problem, it's only 6 rows. So this has a rank of 6. It is actually a rank of 6. You know, you can go ahead and make sure that all these rows are linearly independent. But this guy put a vector on it. lives in R9. And you're not going to be able to invert this matrix unless it has a rank 9, and unless you have a rank 9 matrix. So you could ask, well, what could I do? Well, you could say, well, maybe I can just add up everything all together. So if I add, say, 1, 1, 1, 1, 1, 1, 1, 1, 1, and then what would that give me? 1, 2, 3, 4, 5. I say put 5 there. Would this help me? Well, the answer is no, and because that doesn't actually increase the rank. And the way you can see that is that if you just sum the first 3 rows here, it gives you this row, which means that there's no new information gained there. Okay, so that needs to go. So what else can we do? It's clear that just using the 6 values that you get from rays passing in these directions isn't enough. So we're going to need more angles. And since this is sort of a discrete problem, we can go ahead and do it this way, where I can say that one of my angles is going to be this guy. And so although you could sort of separate these out a little bit. So I'm going to say we're going to need one more row, where you have a 1 in the x1. That's 2, 3, 4, 5, 6, and then 8. So that'll be one row to add. And this hitting on x is going to give us 3. And then, let's see, so let's get rid of that. Now the next row I would hit would be this one, which would hit here and then there, just sort of wrapping around. And this is going to be 0, 1 there, 0, 1 there, 0, 0, 0, 0, 1. And so then this hitting on x is going to give us 0. And finally, we're going to, oops, didn't I do that? Talk about the main diagonal. And so this is going to be 3, so 0, 0, 1, 0, 1. And then I go 7, so we have 5, so 3, 5, and 7 on x. And this is going to give me 2. Okay. So now all of these columns are actually linearly independent. And so if you add this to the system, and you get a rank 9 matrix. You can solve for x. Okay, so that sort of just gives you the general principle. So we see that using an X-ray emitter from this side and just from this side isn't going to be enough to ultimately get all the answers of everything that's inside. But if we use different angles, and so here we used a wrapping here, but I mean, like, there's you can see how you could adjust that if you only counted this one and then you only counted this one separate. That could work too. I just wanted to be efficient. But yeah, so then it'll give you a rank 9 matrix, and then you can invert that. So yeah, so that's the general principle, and so so our method will take a continuum of angles to determine sort of the absorption function. So I don't even know what that last word is, function. I'll just put FN. Yeah, so basically the idea is that, so here we had sort of a discrete function. So you can say that this would be the point 1, 1, this would be the point 1, 2, this would be a point 1, 3, etc. and then x1, x2, x3 was basically f of x, f of each of those points. And so by using all these different angles, we were able to determine what f was when f is discrete. But in the long run, we would like to be able to do this continuously. Now, obviously, using a finite number, we're not going to be able to actually do a true continuum because, we only have, this is, we have discrete samples. And so, so ultimately, we're just going to basically have a whole bunch of samples like this, and then we'll use sort of approximation theory in order to give us guarantees on approaching the right answer. And this is more or less the work that Radon did back in the day. He showed that if you do everything on a continuum, that'll work. But then later on, people in the 1960s and 70s realized that obviously you can't do this on a continuum, but you can do it sort of piecemeal to and you can do this discretely in order to get an approximation of the continuous function. Okay, so let's talk about Beer's law. And so this is Beer's law, that we're learning during the coronavirus, and I swear they're unrelated. Although there might be some absorption of beer in this whole thing. Okay, so what is the idea? We are talking about X-ray beams, and these come with an intensity, and this is what we're going to call I. So basically, there's going to be, and where does this come from? So you have a number of particles, say nx is emitted, and at an energy level of E. So then you basically come up with this Ix is equal to E times Nx. And that is your intensity function. And basically what we're saying is that this is the number of say, photons traveling through X at a point in time. So, okay. And so we're going to make certain assumptions. We're going to assume that the X-ray is of zero width. We're mathematicians. And that we're basically not going to, we're going to assume that they don't bend and don't spread out. Okay. Yeah, I mean, for the most part, this is a pretty safe assumption. I mean, I'm no physicist, so I mean, what I'm about to say is going to be stupid. But basically, I mean, like, light travels more or less in a straight line locally, and so we're only basically doing these whole, like, X-ray things between, like, and under a space of 10 feet. So it's not like we have to worry about the gravitational effects coming from, anything. Certainly not gravitational effects coming from the head of somebody or somebody's arm. Then we're also assuming that they don't spread out. They are not really going very far. So we'll just assume that there's no sort of diffusion as we keep moving. If anything I said is really dumb, for the one or two physicists we have in the classroom, yeah, feel free to email me and yell at me, but that's fine. Okay, so basically what we're going to say is that so each millimeter of the substance that we're passing through, millimeter of the medium absorbs a portion of of the X-ray, right? And so basically the proportion that it absorbs is dependent on the actual material. So the proportion say is dependent on the material. And in the book, they give this whole discussion on Hounsfield units. And there's a table for this sort of absorption, just to talk about it. We're not really going to have to deal with that. We're mathematicians, and what we're really concerned with is being able to reconstruct sort of what's on the inside. In practice, it is something you'll have to worry about, but for us, it doesn't really come up a lot. So basically what we're going to be having is that, we have some sort of mass that we're going through, and hopefully this isn't a person I just drew. And we're going to be shooting X-rays through it. And basically when we go from X to this new point, X plus delta X, we're going to absorb a little bit more energy. And so we're going to say that that the field gets attenuated, and so we're going to say A of X is the attenuation coefficient at X, and basically what we're saying is that the proportion of all of the protons that will be absorbed in the interval from X to X plus delta X is, we're going to call it P of X, and that is written this way. So P of X, and this is verbatim from the book, by the way, it's going to be A of X times delta X. Or, well, not dx, we'll say delta X. We're thinking of this in terms of sort of discrete jumps. Okay, but now if you want to know the number of photons that are absorbed per second by the medium, it's basically going to be P of X times N of X, and so this is going to give us A of X times delta X times N of X. And then if we multiply this by E, we see that we have A of X times E times N of X times delta X, and so then ultimately what we say is that the approximate change in I is going to be A of X times I of X times delta X, but with a little minus sign because it's going to be decreasing. That way we want to say the absorption is negative. Okay, so I'm saying approximately equal to, because I mean obviously there's a whole bunch of other stuff that's happening in the middle here, and so if we change our delta X, it'll change our delta I a little bit. But if we take delta X to be so letting delta X go to 0, basically what we get is that we get di by dx is equal to minus A of X times I of X. and this is called Beer's law. Okay, so this is a separable differential equation. Yeah, maybe I should put this in my differential equations playlist just so you can see a real life example of how we use this stuff. But yeah, so it's a separable differential equation, which means you can rewrite this as di over I is equal to minus a of x dx. And if we integrate, then we get, say, integrate from, say, where we started to where we end. So let x naught be, say, the emitter. How do you spell emitter? That's a fun word. That's something I should probably figure out here. How do you spell emitter? Emitter. Emit. Be the emitter. There we go. And x1, the detector positions. And so then what are we going to get? So in sort of one dimension, what we're going to have is we're going to have the natural log of I at x1 minus natural log of I at x naught. And this is going to be equal to, well, whatever that is on the other side. We don't know what a is necessarily, so that's all we got. x1, x naught to x1, and at x dx. Okay? Now we can do a little bit of extra stuff. We can use the fact that the difference in natural logs gives us a quotient. So we get natural log of I of x1 divided by I of x naught is equal to minus the integral of x naught to x1 of a of x dx. And I see some books go ahead and write this out as I of x1 is equal to I of x naught times e to the minus integral of x0 to x1 of a of x dx. Okay, so there you go. So that's Beer's law. And so so let me go ahead and take a look at a couple of examples. So let's see. So the first example is basically we're going to be sending just one-dimensional functions. So we're going to send a X-ray beam here. We're going to have a detector here, and so say it's going to be at x1, and it's going to be at x2, right? Now let's assume that in the middle we just have sort of a constant absorption. So from here to here, it is some medium, and the absorption a of x. So this line here, we'll call it a of x. We'll assume it's constant, right? So basically what we get then is we get the natural log of I of x1 over I of x naught. And later on, maybe we'll just call this I1, I naught. And is equal to minus, say, we'll just say this is at height a. So it's going to be a times x1 minus x naught. And if I just want to keep things cleaner and get rid of that negative sign, I can also say natural log of I of x naught divided by I of x1, just flipping this, is equal to a times x1 minus x naught, right? Okay, so that's a pretty simple example. So yeah, and why don't we just go ahead and take this as a convention so we don't have to keep thinking about the negative sign. So we're going to say I naught over I1 is equal to the integral from x naught to x1 of a of x dx, right? So let's take a look at another example. So here, let's see. So I'm going to have this function. We're going to say a of x is equal to 1 minus the absolute value of x, for the absolute value of x being less than 1, and 0 otherwise. It doesn't matter where you put the equal sign, but we'll put it there. So basically what does this give us? This gives us this sort of a triangle, and so then this is going to be our emitter, and this is going to be our detector, and so then basically what we're going to be doing is performing an integral. So then what do we get? So the natural log of I naught over I1 is going to be equal to the integral from x naught to x1 of, say, a of x dx. But we know that this is really, the absorption is 0 outside of this, so we can chop this down to just negative 1 to 1, and it's going to be the integral of 1 minus x dx. And since this is 1, this is negative 1, and this is 1, we can see this is a triangle of height 1 and width 2, and so the total integral here is going to be 1. And so there you go. And that is that sample there. Okay, so what we could do is we could also ask, so we're just asking here what the ratio of these intensities are. We could also ask what is I of x, just to be instructive. And so if we're trying to find I of x, then this should be equal to I of, say, x naught times the integral from x naught to x of a of x dx, with a minus sign floating around here. And is that right? Should be right. And then what we're going to do is we're going to just say that we have the initial condition of the intensity I of, say, x naught should be equal to negative 1, right? Or just 1, sorry. Okay, so let's see. And we'll assume that x naught is less than, it is less than negative 1. Okay, so then what are we doing? So this is going to be x naught. This is going to be negative 1. Boop. Gets up until it hits 1 up here. This is at 0. And then it goes down until it hits 1, and then 0 afterwards, right? And so we're going to be looking at, say, whatever it is. This is x, and so we're going to ask, yeah, what is that intensity? Okay, so we can go ahead and work this out. This is just, say, a calculus problem, right? So so it's going to be I of x. Oh, my mistake. This should have been up here, e and minus sign. Didn't get much sleep last night. Well, there we go. Okay, so then let's go ahead and work out what this integral is going to be. X naught to x of a of x dx. Right? Well, we know whatever it is really don't have to worry about it until we get to negative 1 ax dx. And so so the first thing we're going to do is we're going to assume that x is less than, say, we're going to assume that x is between negative 1 and 0. And that's easy enough to figure out. So basically we're going to have negative 1 to x of, say, 1 minus absolute value of x dx. And yeah, just basically geometrically, we're going to see that we have x minus negative 1 as a base of a triangle times 1 minus absolute value of x, and then we're going to divide by 2, right? And so so this is 1 minus absolute value of x, right? And that's going to give us our integral. So we have x plus 1 times 1 minus absolute value of x divided by 2. Okay, so we can go ahead and put that in there. So so the intensity of x is well, if x is less than -1, then it's going to be e to the 0. So so to start, we're just going to be starting with an intensity of 1 for x naught being less than x being less than -1. And let's see, for between -1 and x and 0, we are going to have e to the x plus 1 times 1 minus absolute value of x divided by 2. And we're going to have a minus sign in front of that. Then if we have 0 is less than x is less than 1, then we can figure out what that integral is going to be. It's integral from -1 up to x of 1 minus absolute value of x dx. And yeah, so we already filled in this left triangle, and so that is going to be 1 times base of 1 divided by 2, so that's going to be 1/2 plus, and then we're going to be wherever we are over here. Let's see. So that is going to be, well, it's going to be 1/2, and then minus basically whatever chunk we haven't gotten to yet here. And so it's going to be a width of, say, 1 minus x times 1 minus absolute value of x divided by 2. Right? And so then this next piece is going to be -1/2 plus 1/2 minus 1 minus x to the 1 minus absolute value of x divided by 2. And this is for 0 is less than x less than 1. And then after we've gotten through the entire thing, x being bigger than 1, we can just use this result back here. So basically, we know the integral of a is just going to give us 1, and so so it's going to be integral from, say, -1 to x of 1 minus absolute value of x dx is equal to 1. So this gives us e to the minus 1 for x bigger than 1. Okay, so there we go. That would be the intensity function. Now, this is just sort of an exercise, obviously, in just basic calculus. And the idea is that we don't have this information. The only information that we're really ever going to have is this guy at the end. You could go back and use the intensity to find use Beer's law in order to find the a of x, but we don't actually have a whole bunch of detectors through somebody's head or something like that. So we don't have detectors at each one of these points here. So we can't figure out what I of x is inside. We can only figure out what I of x is here and here, initial and the final. And so the whole game is that only samples that we're getting is this integral itself. And then we want to be able to back out the rest of everything else. And so this is what leads us to the Radon transform. Okay, so the Feynman book puts forth several statements at the end of the section, which I thought were handy. And so let me go ahead and outline what he says. So he wants us to address what we can measure, what we want to know, and then how do you go from this one-dimensional picture to 2 and 3 dimensions? And finally, what is the fundamental question of image reconstruction? Right. Okay, so let's see. So what can we measure? So what we saw before, we couldn't actually pick up, you know, I of x. That's just not possible. With this one canned example where we knew that a of x was just 1 minus the absolute of x, and we knew what it was, we could go ahead and compute it explicitly. But the only thing we can measure is the change in intensity. The change in intensity between the source and detector. Right. What do we want to know? Ultimately, we want to know is the value of a of x at each x. But in this one-dimensional example where we just have, we can just pass through it here, that's not going to really give us a whole lot of information. We know the average value of a of x over that interval, but we don't really know anything else. How do we get from 2 to 3 dimensions? It's going to be, we will consider integrals along lines in 2 and 3 space. And then the fundamental question of image reconstruction is, can we reconstruct the function a of x, y, z, when we think of this as putting it into 3 dimensions, if we know the average value of a of x, or just say a, along every line that passes through the region. Right. So say in 2 dimensions, basically if we know the average values along all these points, along all these points, along all these points, and just basically take every single possible angle that we can, and etc. Can we remake A? And to a certain extent, this is possible. Just to maybe a cleaner figure. And so that's really this is a question. And this is really the content of Radon's work in 1917, I think. And he was the first one to really address that question. But it was later independently brought up by others in like between 1940s, 50s, and 60s, and 70s. So, okay. So let's go ahead and talk about lines in the plane. All right, so basically, taking a look at the plane, we're going to have some line going through it. And basically, the idea of how we want to describe it, we want to do this all in polar coordinates. Right, and so generally speaking, in terms of xy, if we take a look at the ray coming out of the origin that intersects this guy at an angle, or at a right angle, and leaves us with theta, whatever this value is, t, the point that would be our radius, and the point that corresponds to this would be t cosine of theta times t sine of theta. And so then we can actually describe the entire line based on this point, t cosine theta t sine of theta, plus s, which would parameterize the line, times the vector times everything, a vector that is perpendicular to this ray, which would be minus sine of theta times cosine, comma cosine of theta. So and so then this here basically we make a set notation out of it. So we talk about S and R. This would basically describe the line that we would call LT theta, right? So, that is a parameterization of this line, and so this is obviously these points are all in Cartesian coordinates, and but the line we are labeling a line in terms of polar coordinates, and that's going to be really important later when we talk about the Radon transform. So, something that we can say is that if you were to pick any point AB, so for any point A comma B, and say R squared, there is a unique, so for a fixed point in AB, there's unique T and S in R such that A is going to be given by T cosine of theta minus sine of S times sine of theta, and B, which would be given by T sine of theta plus S times cosine of theta, right? And so we have this sort of correspondence. It's kind of basically what we're saying is that for each fixed theta, we're basically going to get a vector along this way and a vector along this way, and we can basically describe any point in the plane by a combination of those two. So what this says is that if we want to take a look at, say, the integral of L of t comma theta of A of, say, xy, we're going to end up getting this. It's going to be the integral from s going from a negative infinity to s is equal to positive infinity. Usually I would just put negative infinity to infinity, but just for clarity, of A times t cosine of theta minus s times sine of theta, comma t sine of theta plus s times cosine of theta, and then we need to worry about what goes here. And what you can see is that if this is basically our x and this is our y, then we have the square root of dx by dy squared plus dx by ds squared and dy by ds squared. That is going to give us the square root of minus sine of theta squared plus cosine of theta squared, and that is just 1. And sorry, this should all be by ds in our change of coordinates. And so then we get this. So all that goes here is just ds. Okay, so so this is going to be really important. Basically what you're seeing is more or less the radon transform. And so, yeah, so ultimately the radon transform of a function in r squared is given as the function say r of f of t comma theta is equal to the integral of L of t comma theta of f of xy. Okay, where we're suppressing all the parameterization in terms of s. And so this is basically the radon transform. And so the whole idea, the goal, is to reconstruct f from the values of the radon transform. And in practice, we get these values of the radon transform through X-ray emitters and X-ray detectors. And so, so now what we're going to do is next time we're going to go through some simple properties of the radon transform, show a bunch of examples, a little bit in MATLAB, and define what sinograms are and everything else like that. And then after that, we're going to go into a lot more mathematical depth, and we're going to talk about the Schwartz space, space of rapidly decreasing functions, so that we know when we can actually define the integral over this function f. I guess, yeah, so that's a good place to stop for now, and yeah, thanks for watching.
Okay, so yeah, that's that. I hope the lecture came out coherent. I am really not 100% confident with this particular material. This is the stuff that isn't mathematics, and so so it's the stuff that I'm not exactly an expert on. But you know, I can read, and I do my best. In any case, so next we're gonna get something that's a little bit more mathematical, and this is called the Radon transform. And the Radon transform comes out of the 19-teens. I think it's 1915. I'll have to double check that. Do I have it here? Ha, it's in here. Let me see it. So he has a translation of Radon's paper in 1917 is what time it is. Here, I will show you a picture. 1917. So, yeah, so we'll go ahead and we'll talk about the Radon transform. Someday we'll go through the Radon's paper, but for now we'll just do the basic introduction. Anyway, thanks for sticking here with me, and I swear the next lecture will make a lot more sense. All right, bye.